Okay, so now we're ready to take experimental data and determine the rate law of a reaction. And it's not complicated, but it takes a lot of writing in order to do this. So let us talk through this process. We know that a rate law must be determined experimentally. So what will happen in this class is we'll give you tables of experimental data. You're going to be able to take this experimental data and you're going to be able to come up with a rate law. And the best way for me to do it is to demonstrate it to you, because there is a fairly straightforward method in order to come up with those powers. So here is an example. We have a reaction and we're given the data that somebody collected. And we know we're trying to come up with a rate law for this reaction. So we start with the generic rate law. The generic rate law says the rate is equal to K. We take the reactants. We have NO. And we have the other reactant is Cl2. Okay? We take their concentrations and raise them to some power. And our goal is to determine the power. Now, if we go in and take one of these data points, okay, and put in a rate, and we don't have a constant, and that's not given, put in some concentrations, we basically have three unknowns. We have a K, which is unknown, we have an X and a Y. We would need three equations, and we can come up with three equations and three unknowns, and we can get there. But that would be pretty lengthy as well. So what we're going to do is we're going to determine one power at a time. So when we're trying to figure out, let's say, X, okay, for X, we're going to look for an experiment where the other substances being held constant. Hold the chlorine constant, that concentration constant. Okay, if you can find experiments that hold it constant, it makes it much easier. Now we look over there, and if we number these experiments 1, 2, and 3 there, experiments 1 and 2 are holding the chlorine constant. So I'll put EXP, experiments 1 and 2 are doing this. Now here's really what's happening. In our previous lesson, I showed you what if you change the concentration, how does that affect the rate, and we kind of came up with some equations. I'm kind of doing a similar thing here. For experiment 1, the rate of experiment 1, which is equal to K times the NO for experiment 1, and the Cl2 for experiment 1, I could go in and I could plug my values in, and I will here in a minute. And if I divide that by experiment 2, okay, K, NO for experiment 2, and Cl2 for experiment 2, what happens is I know that, let me get my pen to write a little darker. These are being held constant, so I can get rid of them. These are being held constant, so I can get rid of them. And what that tells me is a ratio of the rates will be equal to the ratio of the concentrations raised to some power. Now I usually don't write all that out. Let me show you what I do. Once I figure out what's being held constant, this is the background information, but I know I'm holding the Cl2 constant. What I will do is I will take a ratio of rates. That pen's not going to write either. Bear with me just a second. This one is, I can tell. Okay, so I'm going to take, for experiment 1 and experiment 2, I'm going to take the ratio of rates, and actually I want to do it in order of the big over the small. So basically I'm doing 2 over 1 instead of 1 over 2, okay? And here's why. It's easier for me to figure out powers when I'm dealing with whole numbers. Okay, so 4.79, that's experiment 2, over 1.19, this is a ratio of the rates. That's what we see here. For concentrations, I do the same order, 2 over 1. So the concentration of NO is 0.50, and the concentration of NO for the other experiment is 0.25, but this is raised to some power, okay? I'm trying to figure out that power. This has been taken out, this has been taken out. Our ratio of rates will give you a ratio of the concentrations raised to some power for the experiments where the other guy is being held constant. When you divide these, you essentially get 4. When you divide these, you get 2. And 2 raised to what power will give you 4? We determine that x is raised to the second power. Now we're going to figure out the y's value. What's really nice is where we can go in for y. Okay, we would like to hold the other guy constant. Okay, hold the NO constant. If you can find an experiment where the NO is being held constant, it makes it easy. Now if it doesn't, you have to go back to here and plug real values in for everything. But if you're going to hold NO, if they have 2 experiments that hold NO constant, and if somebody's designing the experiment, they might as well do a trial where NO is being held constant. So in this case, this would be experiment number 2 and 3, right? Because NO is 0.05. So then we do a ratio of the rates. Okay, and I do the big over the small. That's 9.59 divided by 4.79 and set that equal to the ratio of concentrations. Okay, for the thing we're trying to determine. We're trying to determine chlorine. So we go and look at the chlorine numbers for these 2 experiments, and we have 0.3 as the big value. It's not 0.3. Goodness gracious. Let's try that again. 3.0 divided by 1.5, but that's raised to some power that we're trying to determine, right? So 4.59, 9.59 divided by 4.79 is equal to, this will give us 2. And 3 divided by 0.5 is 2 raised to some power. So what would that power have to be? Y is equal to 1. So now we know the rate law. The rate is equal to K times NO. NO was raised to the second power times Cl2 raised to the first power, and we don't write it down if it's raised to the first power. Now what if we wanted a value for K? If we wanted to determine a value for K, all we would need to do is take this experiment, take this rate law, and take one of those 3 experiments and plug our values in, and then we would get for rate and for the concentrations and get a value for the rate constant. I'm going to see if we can do that here, and I will do it off to the side in this space right here. Okay? So what is rate? Let's take experiment number 1. The rate value is 1.19. What are the units? Molarity per second. K is what we're trying to determine. The concentration of NO for this first experiment is 0.25. That value is squared. And I should write a unit with that. Sorry. It's a capital M. Okay, that's a capital M. Times the chlorine, which is 1.5. And that too is a capital M. Let me pull my piece of paper up here so I can make sure I have all my numbers. I have 1.19 molarity per second, and I'm going to divide these over here. 0.25 molar squared and 1.5 molar. Okay, and that is equal to K. And the value for all of that is going to give me 13, and the unit, well, molarity, and one of these molarities are canceling, but these molarity squares are not canceling with anything, so my unit is 1 over molarity, and it says per second. I just now noticed that in the data, that's hour. So let's change these seconds to H's, okay? And that is molarity squared per hour. You cannot see what that unit is, so I'm going to rewrite it. 13, 1 over molarity squared hour. One of these molarities cancels with one of those molarities, but I still have a molarity squared, and so that's what we're left with. And that is how you determine the rate constant. Okay, so for our next problem, this is a little bit different, not a whole lot different. I have included above the arrow an OH minus. And this is a way of expressing that a catalyst has been added. We'll talk more about catalysts and what they are and how they work later, but it's something that you can add to a reaction in order to speed the reaction up. So it will also be included in the rate law. So for this reaction, if we're trying to determine the rate law, which is what it's asking us to do, in other words, determine the order, we're going to want to know the order of OCl minus. So it's raised to some power. We want to know it for I minus. It's raised to some power. I'll call it Y. And I will also include the OH minus. It's raised to some power, and that would be Z. All right? Now, we have experimental data here, and we can work our way through each substance. So let's do for X first. For X, that's the power of OCl minus. If we could find an experiment where both of these are held constant, it would be great, because it takes them out of the effect of this guy's concentration on rate, and we can focus only on that. So for X, we're going to try to find experiments where I minus and OH minus, let's put an AN in there, are constant. Okay, look at the data. Can you find any experiments where both of those are being held constant? That would be the second column and the third column. Well, if I number them 1 through 5, experiments 1 and 3 are holding those constant. So then I can do a ratio of the rates. So I'm going to do 1 and 3 here. A ratio of the rates for 1 and 3. Look over to the far right-hand side, and I like to do the big over the small. So the rate of experiment 1 over the rate of experiment 3, right? And I have 4.8 times 10 to the minus 4 over 2.4 times 10 to the minus 4. So that's the ratio of the rates. And I'm going to set that equal to a ratio of the concentrations. Make sure I'm doing it in the same order. 1 over 3 for experiment 1 and 3. The ratio of the Cl minus concentration would be 0.0080 over 0.0040, and it's the concentration that we're raising to some power. So this ratio of rates is a 2. Okay, this ratio of concentration is a 2. So what's the power that you raise this to get 2 out? What is the raise? Boy, there's too many 2's in there. What power do I need to raise this guy in order to get that guy? Well, it's going to be to the first power. So now I can replace this X with a 1. All right, now we're going to do Y. All right, for Y, I'm going to hold the OCl minus and the OH minus constant. And if the experimental data was nice to us, we're going to find 2 experiments where those are being held constant. So you're looking at the column number 1 and the column number 3 and looking for experiments where they're being held constant. All right, I think there's more than one choice, so I want to see which ones I did. I'm going to choose experiments 2 and 3. They're the first 2 you run across. Experiments 2 and 3 are holding those constant. Now, I want to do big over small, so I'm going to do the rate of 2 over the rate of 3. Okay, experiment 2 and experiment 3 gives me the big over the small is equal to the concentration of I minus over the concentration of I minus for experiment 2 and experiment 3 raised to some power, which we're looking for the Y in this case. So now let's plug the numbers in. The rate value for experiment number 2 was 5 times 10 to the minus 4. And that is molarity per second. The rate for experiment number 3 was 2.4 times 10 to the minus 4. Okay, the I concentration for experiment 2 was 0.0080, and for experiment number 3 was 0.0040, and that's raised to some power. So this is essentially, it's not exactly 2, but 2, and this is 2 raised to what power? This tells me that again we have a power of 1. So now we know what y is. Y is 1. And so we've got a first order in OCl minus and a first order in I minus. Now for Z. For Z, we want to hold the other two constant. So what are the other two? We want to hold OCl minus constant and I minus constant, and see how hydroxide's concentration affects the rate. So can we find two experiments where those are being held constant? Let's look at experiment 3 and experiment number 4. We have those two held constant and the OH minus is changing. We're going to do a ratio of the rates. So we're going to do a rate of, which two experiments did I say? We're going to do experiments 3 and 4. Okay, the big over the small, right? So I'm going to do rate of 4 over the rate of 3. That's the big over the small. And I need to do the OH minus of the 4 over the OH minus of the 3 raised to some power, which I called Z. So now let's get the numbers that we have. The ratio of the rates for 3 and 4. 4.6, 3 and 4. Yes, 4.6 times 10 to the minus 4 divided by 2.4 times 10 to the minus 4. And then the ratio of the concentrations, doing 4 over 3. All right, so 4 was 1, and 3 is 2 raised to some power. Now this one is a little bit bizarre, and I can't go down, so I'm going to go above it. This is essentially doubling it, okay? This is not doubling, okay? It's 1/2. So what power would I have to raise this to in order to get 2 out? Well, 1/2 to the -1 power, raising something to the negative power does the reciprocal. So that is what the value is going to be for Z. Now, don't want to leave this problem without stating the following. If you cannot find where everything is held constant other than the one you're looking for, you've got to make sure you also include another substance, okay? Take the value, once you know the order of one of them, you can keep on putting it into your ratios. So here I've gotten rid of the rate constant and the other two guys because they're constant and they're canceling out. But if they're not canceling out, you have to include them in your ratio to see how this affects the rate. And you might run into that as you do some problems. Now, we've done the rate law. So now at this point we have a rate law because we've obtained all of these values. What I want you to do is take one of these experiments and I want you to determine the rate constant value, okay? So here are some choices here. I'm going to give you multiple choice here. Stop, do a calculation, and select the right answer for what the rate law is and what the value of K is. Okay, did you get C? Now that would be this guy right here. And if you take any one of these experiments, it doesn't matter whether, let me back it up, it doesn't matter whether it's experiment 1 through 5, it is a rate law. It has to obey for all of them. This is a rate constant, it has to be the same value for all of them. Plus or minus experimental error. Remember, these are experiments. There's measurements involved. There's going to be little variations. But you're going to be able to obtain a value for K, and it'll be the same for all values. Now, there's two different ways I've expressed the rate law. B's rate law is correct, okay? where I have put a slash there. That means divided by. So it's K OCl minus I minus divided by OH minus. That is another way of expressing the same thing you see in C. So if something is raised to the -1 power in the numerator, that's the same as raising it to the first power in the denominator. Got one more question for you. What is the overall order of this reaction? Well, that would be 1 plus 1 plus a -1, so it would be first order overall. Okay, so what's up next? We know what rate laws are. We've learned how to come up with rate laws. We know that if cars travel at a certain speed, let's go to our analogy of cars going a certain speed. If I'm traveling 65 miles an hour, that's the rate I'm traveling. If I know where I'm going to and I average that speed, I could figure out how much time it takes me to get there. So our next thing to get into is discussions about time and concentration rather than always talking about rate, speeds, and concentration. So that will be our next lesson, is seeing how we can incorporate and calculate time.